All right, it is 2, so we'll get started here. Some notes to make about the schedule coming up. So next week, Friday, test 4. And this is the last PowerPoint for test 4. So Monday, Wednesday, anything we cover there will be on the final exam, but not on test 4. About the final exam is cumulative. So anything we've talked about so far in class can show up on the final. So make sure you look at the old tests and all of that to prepare. The final exam, the way it's going to go is that on May 6th and 7th, it will be open. So it opens at 12 a.m. May 6th, closes at 11:59 p.m. May 7th. So you have any time in those 2 dates to take it. Make sure you give yourself time. Don't wait like at 11:30 p.m. on May 7th and be like, oh no, I can't take it. Dr. Andrews, please extend the deadline. Yeah, don't put me in that position, please. Don't put yourself in that position. And I think you have like 2.5 hours to take it. I think that's how long our exams are. I have to double check that, but I'm pretty sure that's right. Yeah, so that is where we're going for the rest of the semester. So let's actually talk about our topic for today. And this whole last week, we've been talking on the concept of enzymes. So the last couple of lectures, we just have been focusing on, enzyme, I was going to say mechanics, but it's not mechanics. We're looking at how enzymes are actually working, right? And now we're going to be focusing in on the kinetics of enzymes. How fast do enzymes move? And to describe this, we're going to follow Michaelis-Menten Kinetics. Michaelis-Menten Kinetics is an idea. It's mathematical equations created in like the 1930s, used to describe how fast enzymes will do their reaction. Now, not all enzymes follow the Michaelis-Menten Kinetics as we're going to lay out today, but a lot of them do follow it, and it's also a good way to understand how enzymes behave. So before we jump in, let's just start in the top left with our equation. And this is our basic Michaelis-Menten equation. We have E, so this is free enzyme. So this is enzyme not bound to anything, plus free substrate. So this is your substrate that is not bound to anything as well. They can come together to make an enzyme substrate complex. So they are now interacting. This has a speed or rate of happening that we call K1. So K1 is just a variable. It's just a speed. Think of it like miles per hour, but instead it's like, how often or what is the likelihood of this happening? K minus 1 is the reverse rate. So we're going to assume that for our reaction, that the enzyme substrate can form a complex, but it can also break apart to go back to free enzyme and free substrate. So that's one thing ES can do. They can go backwards. It can also go forwards to make product plus free enzyme again. So it can change its substrate to make a product. And this has a rate of K2, right? So this is just another speed. So that is our basic equation. Enzyme plus substrate goes to enzyme substrate complex, goes to product plus enzyme, realizing that the enzyme substrate complex can break apart. And we're going to be talking all about kinetics. So we're really focusing on speed here, speed of reactions. And so that's where we have this V naught. This is initial velocity. And when doing kinetic experiments, people usually only measure initial velocity. That is the velocity right at the start of the experiment. And the reason for that is that initial velocity, or velocity in general, is based on how much substrate you have, right? So if I'm doing an experiment in the lab and I add substrate to my reaction, I know how much substrate is there because I added it. So I can calculate initial velocity. However, if the experiment continues to run, then I actually don't know how much substrate's there anymore, because some of it is making product and some of it is in the enzyme substrate complex, right? So that's why we only care about velocity at the very beginning, because we can actually measure it. Now, our initial velocity is equal to Vmax. This is maximum velocity. So how fast our enzyme can theoretically go, multiplied by the concentration of free substrate, divided by this Km. We'll talk about Km in a minute. Actually, I'll talk about it right now. Km is called the Michaelis constant. And what that means is the amount of substrate needed to go 1/2 your maximum velocity, 1/2 Vmax. So it's the amount of substrate you have to add into your reaction to go to half your maximum speed, right? So that's on the denominator plus free substrate again. All right, so this is our equation to determine initially how fast our reaction goes. And here I have, if the amount of substrate is equal to your Km value, then you're going 1/2 your maximum velocity, which I just listed here. All right, so before we go on with the other stuff, let's look at this graph down here. And the x-axis has been cut off for you. So let me just redo it. So this says 0, this says Km, 2 Km, 3 Km, 4, 5. Right. So how can we actually determine Km through an experiment? Again, Km is Michaelis constant, amount of substrate you need to go to 1/2 your maximum speed. Well, it's actually relatively easy. What you do on a graph is that you have enzyme and you just add different amounts of substrate in different experiments. And you measure what's your initial velocity and you plot it on a graph like this, where you have velocity versus, this would actually be substrate concentration. And from there, you can calculate, roughly estimate what is your maximum velocity, right? If you do enough experiments, sooner or later, your enzyme will be going as fast as it possibly can if you add enough substrate. Once you know the maximum velocity of your enzyme, you go to the graph where you're going 1/2 your maximum velocity. You draw a line till you hit your curve. Once you hit your curve, you drop to the x-axis. Whatever value you read off the x-axis, that is your Km, right? That is the amount of substrate you need to go to 1/2 your maximum velocity. So now that we kind of know about Km, now that we know how to find it on a graph, let's think about what Km means in terms of numbers. So if you have an enzyme that has a really low value of Km, really small Km, what that means is that it does not take much substrate to go its maximum speed. So that's why I have this bullet point here that says if Km is low, then maximal catalytic efficiency is achieved at low substrate concentrations. Put it in simpler English, you don't need much substrate to go very fast if you have a low Km. There's some other terms we need to know about in our beginning to understand Michaelis-Menten kinetics. We have what is called Kcat, which is turnover number. And turnover number is, as I have in these brackets, or parentheses rather, how many reactions do you do per time at an active site? Like, so at an active site, do you do 1,000 reactions like per second, 10,000 reactions per second? That's what the Kcat really tells us. And to calculate Kcat, you take your maximum velocity divided by ET. This is enzyme total. So this is the maximum amount of enzyme you have in your experiment. That's ET. So you take your maximum speed divided by how much enzyme you have in your experiment. That'll give you the turnover number, Kcat, which is how many reactions you do per second. Once you have Kcat and Km, you can then calculate what's called catalytic efficiency, just how good your enzyme is, basically, which is Kcat divided by Km. Here, big numbers mean more efficient enzymes, right? And here's this, and this table is really just a list of some very efficient enzymes and maybe not so efficient enzymes. So one of the most efficient enzymes we have in our body is called catalase. What catalase does is it breaks down hydrogen peroxide. Hydrogen peroxide is something that you create when you do oxidative phosphorylation. So when you make ATP and you're breathing oxygen, one of the side products is hydrogen peroxide, which is not good for the cell, very reactive. So to make sure hydrogen peroxide doesn't destroy our proteins, destroy our DNA, catalase will go and interact with hydrogen peroxide, break it down. And it's very good at doing that. It has a very high Kcat to Km. And it's what we call diffusion control limited. What diffusion control limited means is that this reaction is so fast, the slowest step for this reaction to happen is the enzyme finding its substrate, the enzyme diffusing to the substrate, or the substrate diffusing to the enzyme. So that's our most efficient enzyme, super fast. Anything that's lower to the power 8 or power of 9 when it comes to catalytic efficiency, it's not diffusion limited. So the slowest step is actually the mechanism. But yeah, that's just some ideas of catalytic efficiency. And that was your introduction to Michaelis-Menten kinetics. A lot of stuff, a lot of terms, I know. So this is probably going to be one of those slides that you're going to want to return to and think over, like, what do all these words mean again? What am I talking about? All that stuff. But to get comfortable with these different ideas, we have some problems here. So here I have a table for you. Substrate concentration on this column, initial velocity on this column. What I want you to do is I want you to take a minute and look at this table and tell me, well, you don't have to tell me, write down or think about what is Km based on this data. So let's see if you can remember Km. If not, go back a slide and take a look at it. But yeah, take a minute, see if you can come up with a number for Km. All right, so let's remember what Km is. Km is the substrate concentration that you need to go 1/2, well, I guess that's not equal. It's the substrate concentration you need to go 1/2 your maximum velocity. If we look at this table, we can estimate our maximum velocity is roughly 1200 millimolar a second. You can tell that because if you look at the table, going from 50 to 500 millimolar of substrate, our speed did not change that much. If we go from 500 to 5,000, it does not change that much. So we're basically at our maximum at this point. And I just made it an even 1200. That means if 1200 is our V max, our 1/2 V max is roughly 600 millimolar a second. And then we have to find 600 millimolar on this table. And we don't have it, but we can estimate it, right? It's somewhere between here. So roughly Km, 3.5 millimolar is a decent guess for Km. Anywhere from 3.5 to 4 would be a decent guess for Km based on this data. Remember, people seem, I always get this question, what does Km mean? So just burn it into your brain. Km, the Michaelis constant, is the amount of substrate you need to go 1/2 your maximum speed. All right, so let me pause there. Now we have one question out of the way. Any questions about anything that I have talked about in these opening 20 minutes? A lot of terms there. All right. So here's another question, even though I don't have a label as a question. And I'm going to rewrite this. 1, 2, 3, 4, 5, 6. So here we have substrate concentration on the X, velocity initial on the Y. What is Km? So take a minute and see, based on this graph, what do you think the value of Km is? All right, so let's take a look at this problem then. So the first thing, again, and I'm going to keep hammering this home so you can probably believe I'll have a question like this on test 4. Km is the amount of substrate you need to go 1/2 maximum velocity. So the first thing we have to figure out is, what is our maximum velocity? And this is something that often does not make people happy when I say it. But our maximum velocity is probably 5. A lot of people will be like, well, it's 4 because that's where the graph stops. But if you look at this graph, right, this line, it's still going up. We're not flat yet. And we have not added that much substrate. So this graph would probably just keep going up, small, 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 small. Probably not as fast as I'm doing right now, but it will keep going up till, and I'm just going to guesstimate that it's going to stop roughly at 5. So that's something we have to realize, that in graphs like these, unless the line's completely flat already, we have to know that, oh, we're not at Vmax yet. And so we have to do our best to estimate Vmax. So I'm going to say Vmax is roughly 5. That means 1/2 Vmax would be 2.5. So to find the value of Km, what you do is that you start at 1/2 Vmax, which is what this 2.5 value is if Vmax is 5. You draw your line to the curve. Once you hit the curve, you do your best to draw a straight line, which I'm trying here, until you hit the x-axis. That, whatever you read off the x-axis, is your Michaelis constant. So for us, Km, it's going to be roughly 1.1. And it would have some units, but the units here are cut off. So that's how those two problems, based on a data table or based on a graph, we can figure out Km for an enzyme. As long as we have substrate on the X and velocity on the Y, it should be no problem. Any questions about that? All right. More questions. Yay. So now we're going to do a little bit of math. So let's say an enzyme has a maximum velocity of 2.68 molar per second. And I run an experiment that has an initial velocity of 1.25 molar per second. And I get this 1.25 if my substrate concentration is 0.22 molar and my total enzyme concentration is 0.34 molar, what I want you to determine is Km, Kcat, and catalytic efficiency. So I have the equations up top. This is now your time to try and practice using these equations. So see if you can figure out the questions I'm asking. If you have questions, let me know. Otherwise, I'm going to give you a couple minutes to try and work through this, and then we'll go through it together. But do take this time to try it, and let me know if you get stuck somewhere. So we'll do like 2 more minutes-ish. Again, if you get stuck, let me know. So to find Km, we have to algebraically rearrange the VO equation. That's correct. Let me do that for you. Okay, so it's been a while for people. So velocity initial equals Vmax S Km plus S. So I'm going to multiply each side by Km plus S. So V naught Km plus S equals Vmax multiplied by concentration of S. And since I want to get Km by itself, divide each side by velocity initial at that point to get Km plus S equals Vmax S divided by V naught. Now, I only have one thing left to do, subtract each side by S to get Km equals Vmax S divided by initial velocity minus substrate concentration. Good old-fashioned algebra right there. And since I did all that, let me actually put in the numbers, right? So Km is equal to maximum velocity, 2.68. Actually, let me do it over here. I'm running out of space. Km equals maximum velocity, which is 2.68, multiplied by our substrate concentration, which is 0.22, divided by our initial velocity, which is 1.25, minus our substrate concentration again, which was 0.22. When we do that, let me just double check my math here. Your Km is equal to 0.252. And the unit should be molar, because the units of Km are the same units of substrate concentration. So yeah, once you, the hard part about figuring out Km is just doing the algebra, right? Using the tricks of math to get Km by itself. Once you have Km, everything else in this problem's kind of a breeze. Well, Kcat you can solve without having to deal with Km, right? Because Kcat equals Vmax divided by ET. Well, Vmax was given. It is 2.68. The enzyme total in our experiment was 0.34. Again, let me just double check my math here. Yep. So our Kcat is 7.88. And our units are inverse seconds, 1/seconds, weird unit. Then once we have Kcat and Km, we can do catalytic efficiency because we just divide the two numbers. So it's Kcat divided by Km, which is 31.31. And that is our catalytic efficiency. So that's how, with this information in these equations, and by the way, I'll probably give you these equations on the test, so you don't have to memorize them. But that is how we can use math, the power of math and friendship, to figure out Km, Kcat, and catalytic efficiency. So any questions about going back to algebra or anything up to this point about our kinetics, what we're doing, what these variable means, anything? Now, back in the dark days, before we had computers, if we were doing experiments and we wanted an accurate measure of Km and Vmax, we had to use what's called a double reciprocal plot, or specifically the Lineweaver-Burke plot. And what a Lineweaver-Burke plot is that instead of doing velocity versus substrate, you do 1 over velocity on the y and 1 over substrate on the x. And the reason why this is a thing is based on everything we've talked about so far. So this is velocity on the y, substrate on the s, or on the x. When you do this plot, you always get a curve. And when we were doing that problem with the curve, remember I said, yeah, on a curve, you just kind of have to guess what Vmax is. And once you guess what Vmax is, you know what 1/2 Vmax is, and you know what Km is. Generally, when it comes to science, you don't want to be in the position of, yeah, you just kind of guess and you'll get an answer. Scientists want to be more specific than that. And so nowadays, with our computational power, it's super easy to do a curve fit on the, or do a fit on this curve and figure out what your variables are. However, historically, we had to use this method, which is called the Lineweaver-Burke, where you plot your data where the y-axis is 1 over velocity and the x-axis is 1 over substrate. And when you do this, you get some interesting information. First off, your y-intercept, where your line crosses the y-intercept, that's 1 over your Vmax. So you have just found your Vmax. Your x-intercept is negative 1 over Km. You just found your Km. Your slope is Km divided by Vmax. So by doing this type of plot, researchers could figure out these kinetic parameters by hand, right? You didn't need any really hardcore computing to do this. Like I said, nowadays you don't have to do this, but a lot of scientists still do this to this day as a way of calculating Km and Vmax. That's your double reciprocal plot, which we call the Lineweaver-Burke plot, because those are the guys who, first put this forward. One of the neat things about science, if you create something, you get to put your name on it. So let's get some practice at reading the Lineweaver-Burke. Here I have some data for our Lineweaver-Burke. Take a minute or two, figure out what is Km, what's Vmax. All right. Hopefully I had time to think about this. When doing Km and Vmax on a Lineweaver work, remember, all we care about are the intercepts. The y-intercept is 1 over Vmax. In the x-intercept is a negative 1 over Km. So what does that mean, the 1 over stuff? Well, on the y-intercept, our value is roughly 1.8. So 1 over Vmax is equal to 1.8. And for any whole number, it's always divided by 1. Like 1.8 is equal to 1.8 divided by 1. Therefore, if I want to find Vmax, you just take both sides of the equation and you flip the numerator and denominator. So Vmax divided by 1, or Vmax, equals 1 divided by 1.8. So you see the tricky math I did there? Remember, in math, you can do anything you want as long as you do it to both sides of the equation. So I just flip the numerator and denominator on both sides of the equation. And when you get that, Vmax is equal to 0.555 repeating. And our units, micromolar, so micromolar. And we do the same thing for Km. The x-intercept, let's say that's roughly 2.8, negative 2.8. So we have negative 1 over Km equals negative 2.8 divided by 1. So negative Km equals 1 over negative 2.8. I have a negative on each side, so that actually cancels out, where I say Km is equal to 1 divided by 2.8. 1 divided by 2.8 is roughly 0.357. And our units, you can't see those, but those are millimolar. Right? So that is how you use the Lineweaver-Burke plot to figure out the Michaelis-Menten variables of Km and Vmax. Questions about that idea? All right. Let's see here. Right, so these next two slides are connected. And I don't think I'm going to have time to talk about them in the next 4 minutes. So what I will say here is that Michaelis, or the Lineweaver-Burke, this will be the end of test 4. Exclamation points. Anything, excuse me, anything past this point, you'll see it on the final exam, but you will not see it on test 4. All right. So yeah, so we'll call it a week here, our last full week of classes. Our last Friday lecture, that's next week Friday, you have that test. So yeah, if you have any questions about anything, always let me know. If you need tutoring help or help on any concepts, let me know. I've been sad and lonely all by myself here, nobody to talk to me. Well, I have my wife, so. For the study guides, you skipped number 30. It went from 29 to 31. Is an injust correct name on the document? Also for the final exam, we'll reviewing the last 4 exams help out. What should we expect for the final? Side note, I emailed you extra credit. Yeah, so the extra credit, the way extra credit works is I have that written down, right? And I'm going to apply it to your worst scoring test. So that will be applied at the very end of the semester. The other questions. Sorry, guys, I skipped number 30. I'm going to double check that because I don't know off the top of my head if I did that by accident or not. Sounds like that would have been an accident. So I'm going to write that down and take a look at that. What else? The final exam, while reviewing the last 4 exams, help out. Yes, the final exam is cumulative. A good way to study for it is just like try and retake the last 4 exams and see if you still remember it, right? If there's a question that you don't know how to do on the last 4 exams, make sure you study that topic, because that's how the way I'm going to make the final exam is just like kind of looking at what I asked you for the last 4 tests and just ask you it again. What should we expect for the final? Those 4 tests kind of combined. Everything we've gone over in this class is fair game. Basically, to help you out, if I ask a question on it on one of the 4 exams, you should be prepared to see a question similar to that, or at least talking about the same thing on the final. That means I'm not going to rehash the question. Like I'm not going to copy and paste, but you will probably see that question, that topic again asked. Maybe a different way, but it'll be the same topic. And while I have you, since we do have a minute, let me just double check that study guide stuff. It'll just take me like really just a minute to do that. Course content. Test 4. So you guys 7, right? 29, 29, 30. I see study guide 30. It's there. It's between problem set 30 and 31. Unless I mislabeled the file, let me actually look at the file. Okay, let's move. Catalase different. Why do enzymes add and then 31? No, it looks, just by my looking at it, it looks fine. So if you want to send me a picture of exactly what you mean, like if you can't see it on your end for some reason, but I see it. It's in the test 4 folder. Yeah, just take another look and let me know if it's still not there for some reason. Like send me a screenshot, because what I'm seeing on my end might be different than what you're seeing on your end. But yeah, other than that, I actually, so I think, yeah, okay. I'll put up one homework for this. This will be the last homework of the semester, because this homework ties directly in the test 4. So I think it's good to give you an opportunity to try and do those problems related to today's lecture. But next week, since the in-class time ends on Friday, like May 1st is the last date, I don't want to assign like homework that will, okay, this is what I'm going to do. Sorry, thinking of this on the fly. I will assign homework on Monday and Wednesday, but it'll be extra credit in that you don't have to do it. But if you want to do it, I'll just add extra credit to your homework score. So yeah, that's how we're going to handle it. So the homework that's going to be due next week, Friday, will be, you have to do it. I will assign homework for the lectures we do on Monday and Wednesday. 100% extra credit. If you want to do it, great. If not, I understand, because it's the end of the semester. And I'll make an announcement probably with all this stuff on here. But yeah, other than that, I don't think I have anything for you. So as always, if you have questions, want tutoring sessions, anything at all, don't hesitate to ask me. That's what I'm here for. But yeah, hope you have a good weekend. Study hard. Hopefully I'll see you on Monday. Take care.